all. So this is our lecture number 23 in Mechanics of Materials course. And so today we'll be looking into the behavior of thin wall pressure vessels. Here are the basically two examples that are fundamental for us. So the cylindrical shape of the thin wall pressure vessel and the spherical one, and a quite typical geometry for that. So here where the concept of plane stress that we discussed becomes an important thing. So that we directly will apply that into calculation of these pressure vessel structures. So one of the features here is that because of the small thickness, these structures offer very little resistance against bending, and so so we don't have really significant internal forces that attach to the surface, and so that exactly translates to what we discussed about plane stress. So when the forces that we translate into stresses are in plane, and we don't have out of plane component of that. So in that sense, we will be dealing with the with plane stress state. And here is just to summarize it again. So we have these only tangent components of the forces and corresponding stresses in these structures. So now let's look into more details and sort of some simplification, and we'll start from a cylindrical pressure vessel. So what we have here now, again, so that we have a small thickness T, and so inner radius R, and so here's our coordinate system X, Y, Z. And so what we do, we apply some internal pressure, and as a result of that, as we discussed, we'll have a plane stress state, and so we'll have sigma 1 and sigma 2. Sigma 2 will be in the longitudinal direction, and sigma 1 will be in the what is called hoop direction or hoop stress. So, so what we're after is essentially we want to find this sigma 1 and sigma 2. So that's our assignment. We want to connect it to the actual load, to the actual pressure that will be in that pressure vessel. So let's start from the sigma 1, which we already called hoop stress. Right? So that's in a perpendicular direction. And so here we have our typical cross section, and what we will be doing here is a very trivial step. So we again will use our equilibrium condition, equilibrium equations that we will write in the direction Z. Right? So that then if the structure is in equilibrium, and so then we need to to forces that act in this direction to be in balance. So now we can look into the type of forces that we have here. So so we have the first of all, let's look into stresses. So the acting in this direction Z. So basically that will be the stress multiplied by this small area right here of that acting on that thickness. And in fact we have two contributions, right, on the upper and the lower part here. Right, so that will be the first part that acts in one direction, pulls it so that the rest of the material pulls it together, right? And so what the action of the fluid inside will be the force that is exerted by the pressure, right? So that's the whole force acting here, P multiplied by the area, and so that's exactly here. And now we need to calculate these areas, right? So for sigma 1, our area is just delta x multiplied by delta t, and we have two of these contributions, so that's the factor 2 here. And for p, the area will be this element here, right? So we take delta x, and then we have a diameter. Inner diameter, basically O2 radius, right? 2 are here, delta x, so that's the area that the fluid inside compresses, pushed in direction Z. So that's the area. And then obviously now that our equilibrium equation, we already have the connection between sigma 1 and P. And so we can eliminate delta X here and transposing P to this side. And so the factor 2 is also is eliminated. And so we end up with a, with a pretty compact formula that says that what is the stress in the hoop, so-called hoop stress as a function of the applied pressure P, and here are the geometrical parameters, right? Okay, so that's with sigma 1. Now let's look in sigma 2 in the longitudinal direction, longitudinal stress. All right, so so here is how that will look like for us. So again, we need to account for all the forces that act in the direction x here, right? So that's our equilibrium here. And now let's look what happens, what are forces that act in x direction. So we still have stresses acting on through the thickness here and pulling this back. So the rest of this cylinder pull the part that is on the left back here, and this is equilibrated by the forces that the fluid that is inside pushes in this direction, right? So it pushes essentially here, okay? And so then so the area, so again we need to calculate the whole area, multiply our stresses by that area here, and that will be the force that corresponds to the elastic stresses that develop in the structure. Okay, so so obviously, so that part will be okay. So we just have the area of this of the thickness here, right? So the 2p RT, and now the rest of that is equilibrated against the fluid pressure in this direction and the area of that remaining part here, right? So that's where the fluid pushes back is PR squared. Okay, so that's the area that P that makes that produces force, and the same here. So stress multiplied by the corresponding area, and so we again have the force. Obviously, this for these thin wall structures, this area will be much larger than this area, and similar to what we've seen here too for hoop stress. And so that's why sigma will be. We expect sigma to be of a larger magnitude than pressure. Okay, so now we can simplify. We can eliminate one R here and one R here, and so here is our formula, and pi, of course, also is eliminated. So here is our sigma 2 connected, described in terms of as a function of P, and we have the geometrical parameters, the inner radius, and the thickness. And in fact, what we can see here now is that the formula here for the hoop stress and longitudinal stress is very similar. The only thing here is that we have that factor 2. So the hoop stresses obviously will be larger as we apply P and compare it to the longitudinal stresses in direction x and 2. Okay. All right. So with this, what we what we also can do is we can look into the situation. What happens? This is for normal stresses, but do we have anything? Do we know anything about stresses here? So in fact, we can calculate what is called maximum stress, right? So that is doable. We can do that. So then and so why? Well, okay, it's normal. Some materials will fail when we exceed maximum level for normal stress, right? So that's but some materials are more sensitive to shearing stress and will fail first when the shearing stress, the maximum value of that is exceeded. So that's why we're interested in this situation. Maybe there will be, if we use that type of material, maybe the shearing stress will exceed the maximum level that well. Okay, so we know this sigma 1 and sigma 2, and in fact, an important point here is that these are what is called principal stresses. Okay, so when we have these principal stresses, then we can directly calculate the the maximum shearing stress that will develop here. So if you remember, our formula for that is just take the principle of the maximum minimum values and divide them by 2, and then we will find the magnitude of the shear stress. Very nice. So this is our so if we now take sigma 1 and sigma 2, that will provide us with the calculation of the shearing stress in plane. But remember what we talked about when we discussed the Mohr circles. We actually have sigma 3, which is non-zero, right? So what we can do here, so what we should do if we really want to find the maximum value of the stress, is that we need to to use for the minimum value the value of that zero out of plane stress, right, in direction r, right? So that will be this. And then for the maximum, obviously, we'll take the hoop stress, sigma 1, and then we can just substitute our expression here, that PR divided by T, and so that will be our maximum value for shear for this cylindrical vessel in thin wall structures. Okay, actually the magnitude here appears to be of the same level as the longitudinal stress. All right, so okay, now we're going to look into spherical vessels, and because of the symmetry immediately, right? So we want to calculate the sigma 1 and sigma 2, and there is some pressure that acts inside. But here is the difference with the spherical and cylindrical system. Spherical is very symmetric, and basically the sigma 1 and sigma 2, they must be equal, right? So it doesn't matter in which direction we rotate, we'll choose our small element here. So sigma 1 and sigma 2, there's no reason that they will be different. So we have a very high symmetry for this system. So because of this geometry, we have sigma 1 and sigma 2 0. This is not the case in the cylindrical system that we just considered. Okay, so well, our standard course of action here would be, of course, to consider equilibrium equations. And this is our schematic for that. So we have this cross section, right? So put our axis in direction x, and we will calculate the balance of the forces, and they need to be 0 if we are in equilibrium. And again, so we have two contributions here. So the fluid inside, or some substance inside, pushes this sphere in this direction, right, opposite in the direction of x. And the other part of that spherical shell, this material from this side that we removed, pulls it back, and so to keep it in equilibrium on this tiny a small part of where we have the material, right? And so that will be connected to that sigma 2, and again multiplied by the area, very similar to what we just considered. Still we have the thickness here, and we have the inner radius here. Okay, so we need to just to calculate the areas and multiply the stresses and the pressure that acts here. And so basically sigma will be very similar to what we just calculated before. So 2PRT and minus P multiplied by the area, the projection of the area basically in this direction, because P will be acting, will be pushing in this direction. So we're talking about one direction of X, right? So that's our contribution from pressure in X direction, one particular direction. Okay, so now we can simplify. Pi is gone from here, so we can eliminate one R and R here. And so then sigma 2 will be just PR divided by 2T. And so we remember that they are basically the same, sigma 1 and sigma 2. So then we derived all the stresses in any direction that appears in that spherical shell. Okay, so now why not? We can also look into shearing stresses. So we just calculated normal stresses. Now we want to check what is the value of the shearing stresses. It would appear here. And the same sigma 1, sigma 2 can be considered as principal stresses, and so then we can use our formula from maximum minimum value of normal stress and calculate the maximum shearing stress. All right, so it will not be a surprise here. So that for sigma minimum, we will use our out of plane value, right? Uh, uh, and so that will be 0. So in fact, now if you try to find the maximum shearing stress in plane where the sigma 1 and sigma 2 act, so if you substitute these two numbers, you will find that your shearing stress will be 0. So in plane shearing stress in spherical vessel pressure vessels is 0. Okay, but of course, if we start to look in, for shearing stress and out of plane, and that's what we will do, then we'll find that this is actually a non-zero value, and so that's because we have that zero stress in the direction, so the ditches will be in the out of plane direction here, which is the minimal value of the stress. And then we can just substitute sigma 1, the value of sigma 1 here, right? So then we will end up with the factor 4 in our standard construction, PR divided by T. So this is our maximum value of shear. All right, so so we derived this quite compact and nice formula for stresses in different configurations, and now let's apply them to solve a some examples. Okay, so again, so we start with spherical configuration. So we have some spherical gas container, and we're given the geometry. So this is the outer diameter. So if it's outer, then we will need to adjust a little bit our formula to calculate the inner radius. So that's important to take into account. So the thickness is given, so it's not a problem. We can calculate the inner diameter. And so we are given the internal pressure. And so what we want to do here, we want to calculate the maximum normal stresses and then the maximum shearing stresses in that container. Okay, just to to visualize this a little bit. So that's our configuration, spherical container. So the pressure inside, we know the value, and we know that we have the principal stresses here, sigma 1 equal to sigma 2. And basically, our formula is extremely simple for normal stress, and we also derived that the maximum stress, which is out of plane, right? So here's our numbers. Now, of course, a radius here, that R, is the inner radius, right? So we're given the outer diameter, and so we need to calculate the inner radius. So just if we don't do this, so there will be a little bit inaccuracy in our calculation. And so the radius, of course, will be this half of the outer diameter minus thickness, right? Okay. And that's exactly what we have here. So the half of the outer diameter minus thickness. So the whole diameter was 6, so this is in meters, of course. So 6 divided by 2, so the 3 meter is the outer radius, and minus 6 is 9, which is 9 millimeters. So this is our corrected inner radius. Okay, so which we can use in this formula because our formula was derived based on the inner radius, not the outer radius. All right, so then let's calculate our normal stresses just by using this formula. So we substitute pressure, which is 500 kilopascal, T thickness is given 9 millimeter, and so the radius we just calculated. Okay, so that's exactly what we substitute here. Again, this is our inner radius. So here is our factor 2 that comes from the formula again, and this is the thickness of 9 millimeter written in meters. And so here's our 500 kilopascal pressure applied. And so then our normal maximum stress will be 83 megapascal, right? So that's the value. And now if we look into the state of stress, so that will be that will be our state of stress. So now, of course, again, if we here apply, try to calculate this shearing stress, so it doesn't matter which direction we will choose, we always will end up with 0 stresses, okay? Because these are equal, right? And these are principal stresses. So there is actually 0 in plane shearing stress. but out of plane, the shearing stress actually will not be zero. So we'll find some non-zero value. And basically, well, for that, we already have the formula. This is just one remark that this is out of plane, right? And so we have this our formula, right? So this basically PR 4 divided by T. And then because these formulas are already so similar, that the only difference is just this factor 4 and factor 2 here. So that means that our maximum stress will be nothing but sigma divided by 2, and sigma, this normal stress, we already calculated right here, so we just need to take this number divided by 2, and so that will be our value of maximum stress, 41 and a half megapascal, which is a pretty large stress. It's also normal and shearing stress. So we, if we need to choose the material for this gas container, so then we really need to be careful. And again, just to remind you that these the shearing stress in plane in here in the spherical shell will be zero, and the non-zero shearing stress appears only out of plane. So that's an important note here. Okay, so it seems that we answered all the questions for this example, problem 1. And we now can move on to problem 2, to our second problem. And as you can see, so we move through different geometries. So now we will have a cylindrical system, right? So we have this storage tank, and we have some fluid, actually water inside, and because of that, so there will be some pressure that water exerts, and we need to know whether our design doesn't fail here, so that the pressure that is developing here on the boundary due to the presence of fluid doesn't create too large stresses in the wall, right? So that's what we will be after. So we want to again to calculate the maximum normal stress and the shearing stress. Again, ideally at the end we would like to compare these maximum values to the particular materials that we are using for this design. Okay, let's get to the solution of that. Right, so here that I put just the schematics again. So we have the the hoop stress here and longitudinal stress, and we remember that one of them is larger, right? Probably sigma 1. The hoop stress is larger, and it has a factor of 2 with sigma 2, as we calculated just before. Okay, so and so then, because we know that sigma 1 is larger, and we actually don't really need to calculate sigma 2. For us, we just know that sigma 1 will be the maximum stress, and these two are principal. And so based on this information, we also can calculate shearing stress, and we don't need to calculate sigma 2 for that, right? Let's look into that. Okay, so first, here our formula for that hoop stress, sigma 1, PR divided by T, very compact. And then for the maximum shearing stress here, then we immediately what we will obtain is that the value PR divided by 2T. Okay, but again, this formula calculated based on our knowledge that there is also sigma 3 and out of plane, and this is 0, and so that will be the minimum stress for us. That's 0, and that produces the tau maximum. Okay, so okay, let's look in what we know, what we don't. All right, so thickness is given 5 millimeters, so we don't need to worry about that. Just can translate it into meters. Trivial step. Now radius, and we remember that radius is the inner radius. And let's look if we are given that. Oh, so this is our radius, but it looks like we have the outer radius. Well, then we just need to actually the diameter. We will need to calculate the inner radius based on that 80-meter outer diameter. Not a problem, we've just done something similar for previously, right? So again, half of the outer diameter minus 6. minus thickness, which is 5 millimeter, and so here the outer radius is 4 meter. And so we have that tiny small correction here, so we don't use the outer radius, which is 4 meters, obviously, right? Okay, so we know radius, and our next step is, now next step would be to determine pressure. And in fact, in a direct way, pressure is not given. So what we are given here, that we know that there is some fluid, well, water. So somebody told us, or we remember that we have a certain density of water. This is important, right? And we have the height of the of the tank and maximum capacity, and so we have 14.5 meter. And we're told that actually water fills that tank to the maximum capacity, right? So we can use this value as the for the for the height to calculate the pressures that this water exerts. And so if you remember, then the pressure that water will exert, right? And the way how pressure works, so that will push into here on the bottom the same as here, right? So that's that's the way how pressure would work, right? It pushes in every direction the same. And so to calculate that, we have a formula from basic physics. So that's just rho g h, right? And rho is the density, g is the gravity constant, and or acceleration constant, and then we have the height here. Okay, so this is a given. This is the constant that we also know. It's a universal constant. And so we just put all this together, and we end up with certain value, 142.1245 kilopascal pressure acting here. Well, if this is all this correct, then we just can continue and calculate sigma 1. So this is already trivial step. We just have all ingredients in the formula for sigma, and so we just substitute them. This is our pressure, 142 roughly kilopascal. Our inner radius, right? So to have the precision that we need, and divided by the thickness here. Okay, so in fact we obtain quite high normal stress. So that's we are above 110 megapascal. So this is already something to pay attention to. And as a result, also the stress will be shearing stress will also be relatively high, right? So basically, just I need to take that maximum value and divide it by 2, right? So that's the relationship between these two factors, 2. So our shearing stress is just half of that. Okay, and so then we have we have our shearing stress calculated here. So we have 56.8 megapascal. All right, so very nice. So this is our second problem, and then we will look into one more example, again in a cylindrical case, and we will change things a little bit here. Okay, so we still have this cylindrical shape, this pressure tank. We have the wall thickness, right? Now operating in inches, and so what we also have, we have what is called gauge pressure here. So basically it's difference between atmospheric pressure and the pressure inside. So that's the pressure that we need to calculate in our formula, right? And so what is also different in this example, so we don't have a monolithic cylindrical pressure vessel, but we have here these welded seams that connected different parts here. So that's how it was manufactured. And we are a little bit worried what happens in these connections. So that's maybe that we need to monitor and see whether the stress will not exceed a certain level. So we're given the angle here, so that beta is 20 degrees. And so what we want to do, we want to calculate the normal perpendicular stress, so that will be normal to that welded seam. And also we want to calculate the shearing, right? So, and then again at the end we would like to compare if we are given any information what we can allow or not in this weld to stresses to develop. Okay, so well, our simplification here again is like this. We still have our cylindrical system, so we have sigma 1 and sigma 2. Right, principal stresses, hoop stress, sigma 1 and sigma 2 longitudinal stress, and which we can calculate based on the applied pressure P, which is given. Okay? But then we will need to do something with that because, well, we need to calculate it in a certain direction. But probably we will need to use what we learned from the Morse circle, right? So that's to see how that stress will change at a certain angle. Okay, but let's start from calculating sigma 1 and sigma 2 for now. Okay, so sigma 1 is given PR divided by T, so that's our largest stress here. And we don't forget to calculate the inner radius. So as usual here we're given the outer radius, right? Just to confuse it a little bit. But this is not a problem. We just take again the radius, the outer radius, and just subtract from there the thickness of the wall. Right? So that's what we have. So that will be and we can, okay, we also need to recalculate feet into inches, and so we have 60 divided by 2, so 30 is our outer radius, and then we just subtract here the wall thickness. So here is our number, our inner radius, like a little bit less, but importantly less for the precision, less than the outer radius, which would be just 30 inch. Okay, so radius is known, T is known, so that's the wall thickness here, right? And P, the gauge pressure is also known. So we just can go ahead and substitute and directly calculate sigma 1. Right? So we get PR divided by T. So this is our pressure, this is our inner radius, and this is our thickness. And at the end, so we obtain our value for sigma 1. All the same for sigma 2. In fact, we just need to divide the value of sigma 1 by 2, right? So that's the difference between them. Again, PR divided by 2T, and for hoop stress is just T without any factor here. So sigma 1 divided by 2, and sigma 1 I just calculated here, right? So I don't need to repeat this. I can if I like, but well, we have already this number here, so we just need to divide it by 2, and so that's a lower stress that we have in the longitudinal direction. That we know that, so there's a factor 2 between them. Okay, so basically we resolved the what is called state of stress, so we know what each point here feels, right? And now the only thing is that these principal stresses that we can put on our Morse circle, we need to transform into the certain state which will be 20 degrees from the normal state, right? Okay, here's our state of stress, right? So we have tension applied in all directions, and so there are more tension that is applied in this direction, basically in sigma 1, right? And there are a little bit, well, of this factor of 2, lower tension applied in direction sigma 2. Okay, so longitudinal stress. So this is our hoop stress, and this is our longitudinal stress. That's what they. So okay, let's just remove here from the slide all what we don't need, and just leave what we will need to calculation further. So here's our sigma 1, right? So we just calculated that, and sigma 2, these are given, and what we are going to do, we are going to use Morse circle to see how they transform into the values of normal and shearing stress that act here at an angle at this weld. Okay, so again, we were going to use our Morse circle. Let's build that. So it's not a problem because we know the the our principal stresses, sigma 1 and sigma 2, immediately we can calculate the central point, the average stress here, right? Sigma 1 plus sigma 2 divided by 2. So that will be our the center of that Mohr circle. And we also can put the radius here to calculate this. And now that will be difference. And because it's principal stress, so we don't have shearing stress to appear. So that will be, these points will be on the axis sigma, right? Okay, so let's put it here. That's our sigma 1 and sigma 2, both positive. So we're in the positive part of the sigma. So there, and so that's where our Mohr circle will be. Okay, so now next step would be just to find that point, that rotation of beta. But if you remember, and we remember that if in physical space we have angle, say beta or alpha, then in our Mohr circle that will translate into 2 beta. So here we have 2 beta, 40 degrees, right? So that's our agreement here in between the physical space and the Mohr circle space. Right, so we rotate it from here to here on 20 degrees. So we're going to rotate our state from here to here by 40 degrees, double of that. Okay, so then we need to calculate the value of normal stress here, that will be point here, and tau, that will be the coordinate of that point here, right? So that's our state of the normal stress that acts on that line here, right? And so that will be in this direction, normal stress and normal direction. But we also will have shearing that will act on this direction. Right, so that will be the value. That is the coordinate on tau. So that will be our shearing stress right in here. Okay, how do we find it? So for sigma beta, right, so that basically we need to calculate the distance from 0 up to sigma beta. That will be our coordinate. That will be our value of the normal stress here. And so what we know here is this. So we know actually this point is that exactly sigma average of the center, and we just need to subtract the this part, right? And so that will be the whole thing from here to the center minus this, and so that will be the length from here from the 0 to sigma beta, right? And so that means that we need to calculate this part, right? And what we are given here is the radius, right? Radius we already calculated here. And we know the angle, right? So this angle is 2 beta. So based on that, on radius, on the angle, we can calculate this part. Okay, and so then our sigma beta will be just sigma average, the whole distance from 0 to the center, minus the radius multiplied by cosine the angle that we have here, 40 degrees, right here. Okay, so this is with sigma beta. And now we are going to do similar calculations for tau. And for tau, it's even simpler because we basically need to calculate this length here, right? And again, we know the radius and we know the angles. So then for tau it will be. But we can calculate first the numbers for substitute the numbers and calculate the normal stress at beta. Okay, so that will be this is the average, the central, right? So that's the distance from here to here. So that we substitute here, and then we use the value of the radius and multiply it by the cosine 40 degrees. And our normal stress will be just this. Okay. Okay. Now already discussed tau, but let's just put this here again. So this part tau of beta will be nothing but the radius multiplied by the sinus angle here, which is 2 beta 40 degrees, and that will appear here. So we now take the radius and take the value of the sinus 40 degrees, and so then we have a little bit more than 1 KSI here for the shearing stress. And basically that's we calculated everything here, right? So then And so we ideally at this point we would use these values of the stresses and ask ourselves whether the particular welding technology produce the welding of good properties that that we can allow these stresses to develop, and so there will be no failure or some crack that will initiate here and then may lead to failure. So these are important numbers for this type of design. All right, so that's it for this lecture. Thank you and bye.